So if I had something like, we saw this the other day, square root of, what you got, Jeff? I don't know. Square root of 15 times the square root of 3. Okay, you could do that.
You can 3 multiply 5. Now we have to it's the similar 3.
Well, you break 15 up.
Yes.
And that's not a bad choice in the first place. But is there 2 of anything in there? No. So there's no part of 15 that I can work with. So then the only thing left for me, and if you do that, you realize you have 1 3 and 1 5. So when I multiply by root 3, I'm getting 1 more 3. I should then be able to do something with that number. So 15 times 3, 45. And of course, that's going to be 9 times 5. Because you gave it that extra factor of 3. You should have a 9 in it now. 15 has a 3 in it. When you multiply by another 3, it obviously has 2 3s in it. 9. So what's the big deal with that? Yeah. So it's radical 9, radical 5. 3 radical 5. Cool.
Oh, you multiplied for all 3.
Is that cool?
Because the only reason you can do that is because they're both in the row.
They're both second roots. If one of them was a cube root and the other one was a square root, I could not do that. Yeah.
I always have a problem knowing which number to leave on the outside. Is it because you can break it down?
It's not. I like that you said that. I have a 9 and a 5. So it's not that I'm leaving a number outside. It's that I'm doing the part that I could do. Can I do the square root of 9? Yeah, so I do it. Can I do the square root of 5? No. But I always get, I'm glad you said that, because I always get somebody to do something like this. They'll break something up, like this maybe, and then the next step is this, or something. Nothing can come out. And it's my unfortunate way of saying it. Because something does kind of come out, but you do something to it. The only way you can escape a radical is to actually have the square root taken, right? Right? So it's sort of like the only way you can escape. Anybody ever see Shawshank Redemption?
Oh, yeah.
The only way you can escape there is to get really dirty. Right? You're not going to come out clean. You're going to come out different. You're going to come out changed. You're not going to be the same person you were before you started to escape. You ever seen that movie? You probably agree. So the only way that something can come out, it was a 9 inside, now it's a 3. It's gone through a lot of shit, and now it's a 3. See the movie, that's even more appropriate. You guys kind of with me? I mean, nothing can just come out. It's the part that you can do the radical, the square root. You do it in there, and you put the answer. I'm just replacing this with what it is. That's all I'm doing. Right, and this is times, because it was times to begin. It was times in here. It's got to stay. That multiplication's got to stay there. Maybe. So, I mean, we saw where this is useful. Being able to do this is useful in something like this here. This is not equal to negative cube root of 38 or something. You guys see where that would have come from? If I put that answer down, do you see where somebody might have come up with this? Maybe even a negative there, I don't know. You see where that came from? So I'm subtracting, Jeff. What the hell do you want me to do? 2 minus 3 is negative 1. 16 minus 54 is negative 38. Right? Math boy. You want me to subtract, don't you? Well, of course, we know. Right? Math nice shirt. But we know, before we can add or subtract anything, we know we have to have like terms. When it's fractions, we call it like denominators, but it's still like terms. Right? So I definitely can't subtract these because they are not currently something I can consolidate. They're not like terms. What can I do to each one, though?
Multiply or factor 2.
Yeah, a really good way to do this is not 4, right?
No.
That is what 16 is, but there's another thing. Cube root, so I need 8. That sounds better. So this would officially, if you want to rewrite this, it's the same thing as 2 times cube root of 8 times cube root of 2. That's the same thing, I just split it up. And then what can I do with this guy?
27.
Yeah, the beautiful thing is now you know the 2 is there. I'm going to try the 2 there. Most of the time it'll work. Especially here in this book. But sure enough, 2 times 27. And 27, thank God, is a cube rootable number. So this is minus 3 cube root of 27, cube root of 2. So I just split it up.
No, minus 9 now.
I love it. So now, what's the cube root of 8?
2.
Times 2. So I got 4 cube roots of 2 minus 3 times 3. So that's minus 9 cube roots of 2, which is
minus 5.
Yeah, so I owe somebody somewhere 5 cube roots of 2. So the insane idea of like terms, which you learn normally when you do polynomials, but are actually another way to look at fractions. You have to have like terms, that's why you have to have like denominators. They can be applied to weird things such as radicals. You have to have like terms before you can consolidate them. Cool. So 2 more things, and then we can get into our review. All right. What do you think you should do there? And the third one. So again, it's a beautiful example of math does not care what you put into something. When it's in that form, I FOIL or distribute, which is even better. Right? I know what to do here. I don't care what's in there. And people always freak out. I mean, if I had to do this, what would be your first step?
Multiply.
2x squared, right? Did you worry about, well, what do I multiply the x by? There's a 2 there and there's an x. Did you even think about that? No. Probably, I didn't even think I could think about that. John, what the hell? Don't say. But, I mean, now look here. People always freak out when they get to a point like this. This first step should be pretty easy. What's that?
21. Square root.
There, square root of 21. Now when I do this, people freak out a little bit.
Yes.
But radicals here are sort of like variables. I don't know what the hell root 7 is. They have to go with the other. I can only multiply 2 things when they have the same root. So can I do square root of 7 times 3 is 21 somewhere? No, 3 didn't have a root. So how could it have the same root? So what do I do here? Yeah, this is plus 3. Comes for the ride, just like the 2 did.
Yes.
Times
3, 5,
root 35.
So you multiply the radical inside, not
I love
the outside?
It's just like what you do when you have 2x times x. You do 2x squared. You multiply the x and the x. Do you worry about the 2? No, it's still there. It just comes for the ride. Right? So what about this part here?
-2, square root 15.
Yeah, just put the roots together. Root 15. And then finally,
Minus 3.
minus 6. Square root of 25. Which you can do, right? Which kind of makes sense. What's the square root of 5 times the square root of 5? 5. Yeah.
Why put square root multiply 5 times square root 5, 25? It's supposed to 5, I think.
Yeah, it will be. What's the square root of 25? 5. Good. But I'm just following what I've been doing here, but I want to point, now I'm going to talk about this. What's square root really mean? What's a square root as a power? What's the square root as a power? 1/2 power. I love it. So it's half of 5 somehow. So when I multiply 2 halves of 5s together, I should get a whole 5, right? They should complete each other. Aw. And sure enough, I mean, so what you're saying right there, Ron, you're saying, why the hell did you write that, Joe? Why didn't you just write 5? And it's because I'm trying to make the point now. That will be 5 either way you look at it. So what's root 11 times root 11? 11. Right? It's awesome. They complete each other. It's really nice. But anything else I can simplify here?
No.
You know you can't break any of these down because you know exactly what they have in them. You multiplied it out. They have 1, 3, and 1, 7, or 1, 3, and 1. I can't do the square root of any of that. I need 2 somethings inside. Don't waste your time, don't waste your time, don't waste your time. The only thing I can do, what's 6 times 5? 30. But I always get somebody go some more steps. They start doing, well, root 21, but that's 56, and the 3. No, you can't put them together unless they're like terms, right? Stop right there.
If we break 21, 7.
I could, but I know going in, I could break this up into 7 and 3, but why? The whole purpose of that is to see if there's any 2 factors in there, right? You with me? Because I can do the square root of 9 because it's got 2 3s. But I know going in it only has 1 7 and 1 3. I'm the one who put it together. So why would I tear it back apart to look at? I already know what's in there. I know it's not going to go anywhere. But if you wanted to, you could break it up and you could see it ain't going nowhere. But I do get people that do this and somehow it becomes that. And that's the whole idea about something coming out. It can't come out. Think about the dude crawling. It can't just come out. It's got to come out changed. So it can't just come out. If you can't do the square root of it, it can't come out. Yeah.
If you can't see the 5, doing the
Yeah.
the 25 to 5, and you leave it like that, is that wrong?
If you leave it like what?
Like 25?
Root 25?
Yeah.
Yes.
Okay.
I mean, technically, it's the right number. But it's sort of like leaving 6 over 8 as an answer. You haven't reduced it. You haven't done more with it. And here's a little worse, because if you do one thing, then it can go with the 6. So you're kind of like leaving some stuff out that you could do. Yeah.
I have a question. If I have like 10 minus square root any number, leave it like that. That's it, or can I complete it?
So if you had 10,
Minus any square root, any. Yeah, that's it.
yeah, they're definitely not like terms. They don't have the same root, right? Even if I made it 10 minus radical 10, I still can't do anything with that. I just have to stop right there. They're not like terms. One doesn't even have a radical. I know they're both 10s, but they're not both 10s, really. Square root of 10 is not 10. Right? Yeah.
What was the breakdown on the 3 and the 35?
Again, you could, but you knew it was made from the 5 and the 7. So when you break it down to 5 times 7, can you do the square root of either one of those? No. So I can't go anywhere with it, right? It's sort of like if I said reduce that. No, I can't, Jeff, right? So, so here, can you reduce this? No, there's nothing inside that can go further. Okay, cool.
If instead of a minus sign on the fourth one, it was a multiplication sign, you would be able to do that, right?
Well, how do you mean?
Oh, you would just put those together, or?
Yeah, I mean, they would just sit there like that.
Oh, okay.
Yeah. Now, if instead it was radical 10 times radical 10,
Just 10.
now I can finally do something.
Just 10.
Yeah, exactly. It would be square root of 100, or even better, just half of 10 makes a whole 10. That's the only one in those 3 that I can actually do something with. Okay. All right. So here's the last thing before I review here. And you guys, in the white book, it's in section 12.4. In the blue book, again, I don't know. Where am I at? 5, 6, 7. Well, way up there on my Roman numerals. Let's see. So, there's a process in mathematics called rationalization. And this is not the psychological one. This is not where you try to rationalize things away. This is... math doesn't like this. Math, in a lot of applications we want to use, we want to be able to put stuff together. And this is really bad. Not only am I dividing by something, I'm dividing by an irrational number. So we have this process called rationalization. Most of the time you rationalize the bottom. And if you think about what that word means, rationalize, it means make it rational. So right now it's irrational. Why is it irrational?
Because there's a root at the bottom of
Yeah, it's a root that I can't do. That will always be a non-repeating, non-ending decimal that goes forever. It's ugly, right? So why can't I do the root of this? I like it. I love that question because you're like, I'm not sure how to answer that, Jeff. It's freaking 7. What else has to be there for me to be able to do it?
The square both sides.
The only thing I can do, I'm glad you said that. The only thing I'm allowed to do to the top and bottom of a fraction is multiply or divide. I can't square the top and bottom. Otherwise, 1/2 would equal 1/4. Because you square both the top and bottom. That's a little crazy, right? So I can't square the top and bottom of a fraction.
Are you gonna multiply the 7 by both sides?
Yeah, exactly. How many 7s do I need inside here to be able to do it?
One.
So it can come out of
It's a second root, so I need one more. Maybe that's what you mean. I need 2 total. So I give it when it's missing. But if I give it a square root of 7 on the bottom, I have to give it a square root of 7 on the top. Not because I want to, because I have to, right? We see that all the time. We see one piece of something. If only I can make that better. But to change that, I've got to change all this other stuff to make it legal, right? So what do you get when you do that? What's 3 times root 7? 3 root 7, 11. No 21s. And what's root 7 times root 7? 7. Sweet. Or if you want to, root 49, which is still 7. And then don't do that. That's crazy. Can't count those 7s. They're not 7s. One's a 7 and one's half a 7. Right? So, what if you had this here? Oh, whatever. Yeah. It's taking that same idea. I always have somebody get the wrong thing from what we just did. They say, oh, you just multiply by the same thing. Why did we multiply by 1 more 7? Because it's a square root. It needs 2. All right, what's going on here?
1 minus 1.
Yeah, it's a cube root. How many 11s does it need total? 3. So it needs 2 more.
2 more.
That's all you're thinking. Don't multiply by the same thing. That won't help us. I'll have 2 11s. That'll suck. This dude needs 3. I need 2 more 11s. So I call this, I actually don't call this, right? I call it completing the root. The root needs 3. It's only got 1, so I give it 2. I complete it. Right? So then on the top I get 2 cube root of 121. That's what 11 squared is. On the bottom I get 11. I love it. Right? 1/3 of 11 and 2/3 of 11 is a whole 11. Or if you'd rather, what's 11 times 11 squared? 11 cubed. Those die. So that's officially called rationalizing the denominator. If you go all the way up, if you're going to go up all the way to calculus, there are certain situations where you rationalize the numerator. We'll pretty much always rationalize the denominator.
Did you get 11 at the bottom?
I did. How?
Yeah.
Because what's the cube root of 11 times the cube root of 11 squared? The cube root of 11 cubed. And the cube root and the cube die. 3 goes into 3 once. Yeah. Is that cool? I mean, hopefully that's kind of come out of this whole discussion. The 5th root and the 5th power are opposites of each other. They're what's called inverse functions. They undo each other. It's just like multiplying into. So if I multiply x and it's being divided by 5, bam. So if a 5th root, some x that's being raised to a 5th power, they kill each other. They undo each other. So then you just get x.
You could still rewrite it at the bottom as like 11 times 11, like which is 21, right? And then just take out the 11 because you know you would just skip that step. Is that what you did? Like 11?
No, I didn't want to do 121 times 11, even though it's just 1331. I don't know the cube root of that, right? I'd much rather just look at it as the cube root of 11 cubed. It's much easier. Yeah.
So always you multiply, but
What you're
you need
missing.
from the bottom?
The bottom, yeah. When they say rationalize the denominator, you look at the denominator. You say, what does he need?
The one.
Okay. So that pretty much that's the couple of gaps from what we did last time. So we're up through 12.5 in the white book. I think that's 7.5 in the blue book. Oh, here's my translation. The 12.5 in the white book is 7.274 in the blue book. Right, so the blue book you got 7.1, 7.3, 7.5, 7.274. That's how far you have to go up. Okay. I got more of these. So now that I got a few more people came in. Anybody else need a practice test? Oh, just a minute. All right. Couple things. Let me see if I remember that I've observed from the homework. What's the very first thing?
Move the 3 to isolate.
Good. The very first thing that you have to do before you start writing your cases is to get the absolute value by itself first. Let's really investigate real quick why that is. What should the answers to this be? What should the answers to this be? 4 or -4, right? If only they were all like that. Now, if I happen to just add 1 to both sides. Isn't that still the same equation? Right? That's the same damn equation. They should have the same answers. But then I get somebody do this. Right? And one thing is the absolute value is still in there. So the minute you start writing your cases, your absolute value should go away. That's the whole point of the cases, is to rewrite it without that. So you're able to move stuff around. But you see, I mean, if you started solving this, you're not going to get the right answers. You'll get this one looks good, but then that one looks bad. You guys kind of with me? We know what the answers to this should be. Just because I add a 1 to both sides, you shouldn't change the answers to the equation. It's still the same equation. So what did this person make the mistake of? They didn't minus the 1 first, and then they would have been fine, right? I really want to make that point. You have to isolate the absolute value. In fact, when you solve equations, you pretty much almost always isolate where your x is. And then you do something. So, do you have to do that? No, there's a whole way you could do it otherwise. You don't have to isolate the absolute value first. It just makes it a little bit harder if you don't. Sort of like this. How would you solve this equation? Oh, you'd isolate where the variable is first. Is that what you're saying? Yeah, whatever, Jeff. I didn't say it. But, I mean, that's basically what you're doing. Here's the absolute. Here's the variable. I want to isolate where that thing is first, so I move that guy first. Now, we really know why that is. I could divide by 7 first. But why do that to yourself? Why bring fractions in? Are you guys kind of with me? So you pretty much almost always isolate where your variable is first. And then start doing whatever you got to do to get it on its own. Okay. Yeah.
If there was a negative on in front of the x, then I would divide.
Like here?
Yeah, there was a negative in front.
Oh yeah. Cool. I like it. So let's make that. So then this would be negative, like that, less than or equal to 6, right? And then if somebody does not divide that negative away, they start writing their 2 cases. When actually, if you do that first, what do you get?
Divide
by
-1.
1.
Bless you. So what do you get?
-6.
Great now.
All right, you get -6. I agree with you. Great. So I see a lot of people forgetting to flip. And what's the beauty of this?
No solution.
Careful. When is an absolute value not bigger than a negative number? Is an absolute value always bigger than a negative number?
Now move the 5 to the...
No.
Okay.
When is an absolute value ever not bigger than a negative number? Give me an example. I don't know if you guys are with me. Is it possible for an absolute value to not be bigger than a negative? That would basically mean it has to be negative itself. Can that ever happen? Whatever x is, this absolute value is going to be bigger than negative 6. I will not give you money. I will bet you money. Right? I don't have much money to do either. But yes, that's why. I know the other way to do this is to replace it with itself and the negative of it. But if you solve for it first, you catch these special cases so much easier. Everybody looks at a negative and just says no solution. But this is saying the absolute value is bigger than it. That's always true. It's always bigger than a negative number. So this is all real numbers. If it said less than a negative, screw it. That's nothing. That's no solution. That's another reason why you want to isolate the absolute value first. You might hit one of these special cases and be done. You won't have any work to do. You don't have to subtract 5 or anything else. You're done. So a lot of you guys missed that when it said something like absolute value x equals negative 9. You said you did both answers and you went to town. And if there's more stuff in here, that would suck even more. But if it says this, what's the answer?
No solution.
No solution. It can't be negative. Okay, cool. Yeah.
Wait, why is it all real numbers again?
Because any number that I put inside here will always be bigger than a negative number. Every absolute value is bigger than a negative. The smallest this could be is 0. Otherwise, it's going to be positive, right? So it's always going to be bigger than a negative number. Cool. Yeah.
It's a topic subject, but for the practice test, the last one says page 499, 2224, and I want to know where that is.
I'm always biased towards the white book, so you got to excuse me on that. We're going to do that together in class, actually, because it's not even on the answer key. So this is the trouble I get into when I try to make things easier. Yeah, so there's a couple of work problems, I think. There was a work problem and a rate problem, so we'll do that up on the board here in a minute. Okay. Yeah.
So what page number is it?
Well, in the white book is 499. And we'll do those problems on the board in just a minute. Okay. Yeah.
I have a question. If I have like a plus 6 over a minus 6, it's already, I can't make it factor. So from the beginning, just as a blind that's it.
If you have what now?
A plus 6. Over,
A plus 6?
Yeah. Over a minus 10.
A minus 10?
Yeah.
So I know you're talking about a specific problem in the book, and the question was, tell me what values of A are not allowed. It didn't say simplify. It said, what values of A can you not use? So now you look at, yeah. No, careful. Negative 6 is fine. It's no problem to have a 0 on the top. It's a big problem to have a 0 on the bottom. So be careful. You don't say this. You don't need to say this, right? In fact, that would be unfair. I can put a negative 6 in there all day. I get a 0. 0 is fine. It's something over 0 that's no good. So then A can't be 10. No good. There you go. Cool. And I think the biggest problem here's the biggest single problem from simplifying these is people getting. Let's see if I can make a problem real quick that'll actually work. There we go. Okay. So the biggest single mistake that I saw repeated across a lot of people's papers. There were a lot of other mistakes, and most of them had to do with not being able to factor something correctly. So if you can't factor something correctly, you're not going to be able to do this, obviously, because it all hinges on you getting the right parts. So you can see what really dies. What form do you have to use on the top? Grouping. When do you know you're done factoring? And what happens here?
But
X minus 3. And why is that, thank God, good? Because that tells you you can finish it. So one thing to realize is, are you done factoring? Bless you. Are you done factoring? Or am I done factoring? You're the one doing it, Jeff. Because I got a minus sign in it. I know I'm not done factoring. Factoring is all about breaking something up across multiplication.
why you make it grouping? You already have minus 3x. Okay, this without a y, yeah. No, it's okay.
That's all right.
I think this is xy.
Gotcha. And on the bottom, of course, it's what? So I had a couple of different things that happened. I had this happening, and then that's still there. That's no good. Why? Can somebody... You know why that's no good? I'm not done factoring, but that by itself is not a good enough explanation. That's sort of a teacher, just do the work. I cannot cancel this out unless I do it in both, and that would be fine. I would still have trouble with it because you're opening yourself up to making more mistakes. But both of these pieces are being divided by this. So if you just finish the factoring, it's going to be so much easier. There's one last step here. And if you have a plus there, you know you did something wrong. These are not the same. You can't do the last step. The last step in grouping is take this piece out. And you can't take it out if it's not the same. So the last step is take that out. And you're left with
X minus y.
x minus y. And now it's a hell of a lot easier to look at this thing. What happens? Yeah, the x minus 3's go away. That's a lot easier to look at. So whenever there was a grouping problem, I had a lot of people kind of stopping too early, not filling enough stuff. Then you're not sure what the hell is left where. And so you just throw down what you see. And it doesn't make any sense. You can't cancel things unless you have opposite operations. Now that makes sense. I've got subtraction, I've got division. No good. I can't cancel things. So just make sure when you do that, make sure you're done with the factoring before you start killing stuff. Okay. Yeah?
With grouping, do the top two have to be the same? Is that like how
These have got to be the same. Or else there's nothing that math can do to help you. Because that last step in grouping is GCF. They both have this thing in it, so that thing can come out. If you don't have the same thing there and there, either it's not factorable, or more likely, you did a mistake here. And most of the time, the mistake is you took a negative out and forgot to change this guy's sign. And when you see a plus there, you see minus there, the math is trying to tell you, dude, you should have made that a negative. You took a negative out. You should make it a negative. Right? What happens when I take a negative out of something? The sign changes. This is positive, this is negative, now it's positive, this is positive, now it's negative. Cool. Okay, maybe. Now, I did also see a few people, so if you did this, I'm not singling you out. I'm only putting up here right now what I saw many people do. What was it, Jen? So you do this step here. But then you put something like this here. And then you thought that was all multiplied together. Maybe something like xy, x minus 3. I mean, it just doesn't follow any logic. I mean, what's missing here? What's missing is a couple things. There should be like a plus sign there. Because you took out a positive y, that's why the signs didn't change. And then you go, oh crap, those aren't the same, I should take a negative out so the signs will change. Right? Not a lot in math does that for you, but the great thing about grouping is it actually has a part that tells you if you're on the right track. That's crazy. The problem itself tells you if you're doing it right. How often does that happen? Not very. So realize that. This has to be the same as this. If it's not, you say, well, did I forget to take a 2 out? Did I forget to take a negative out? What did I forget? Okay. So now I'm wide open to whatever you want to look at. Yeah.
On the top, it has 2B.
2B? 2D. So this one was that ugly root that doesn't go in evenly. And again, it's completely up to you to figure out which way you want to do these kind of problems. I always try to give you the way that's quicker, and I always try to base it on what's really going on. Any fifth root is actually a 1/5 power, so it really is dividing by 5. That's why the shortcut works. But if you don't like the shortcut, you can certainly write them out, right? But how do I always have to do the numbers? The numbers will never act the same as the letters, because the letters are factored, the numbers aren't.
Divide by.
Yeah, what can you do the fifth root of?
64.
For the number?
Yeah, what's 2 to the 5th power, for example?
32.
2 to the 5th power is 32. Hey, bam. Right? 3 to the 5th power, now we're getting pretty high up there, right? That's 243. So you kind of get a feel for, I'm trying to give you an idea of what to do for yourself. When you hit a problem like this, you're not sure what the hell to do. You look at the root, you look at the number, you start writing. If it's a 4th root, you go 2 to the 4th is 16, 3 to the 4th is 81, and you start seeing, do I see any of that in there? That's giving you an idea of how to try to break it up. Right? Well, here, how do I break that up? Definitely.
32 and 10.
Yeah, 32 and 10, because I know 32 is going to work. So I break that up as 32 times 10. So what's the fifth root of 32? 2. So that's why that gets written outside, because it's done. The root was done to it. What's still on the inside number-wise? 10, because they can't do the fifth root of 10. Not easily, anyway. What about the letters? What happens here?
You break it up.
Yeah, you could write A6 as A5 times A. So you know we have an A that's going to stay. And you have fifth root of 5 power goes away. Or you can say 5 goes into 6 once with 1 left over. I mean, I personally think that's so funny that something you learned way back when is exactly that phrasing works again with something really a lot funkier, right? It's kind of neat. 5 goes, you can write B14 as B10, B4. So you can see the 4 B's that have to stay inside. Or you can just say 5 goes into 14 twice with 4 left over. And then does 5 go into 4? No, so they're all left over. 4 little dudes. That's exactly how I would recommend you do that kind of problem. Write what's in it. You write with it. You leave a little space, and if there's too much space, you just put a dot, so I know you're multiplying. You don't have to rewrite the whole damn thing. Yeah.
Where'd the 32 go? I got lost.
What's the fifth root of 32? It must be 2, because it takes 5 2's to make 32, right? That's the whole idea of a root. A root says, what does it take this many of to make this when you multiply them? That's the answer. So since it takes 5 2's to make 32, the fifth root of 32 must be 2. So on the 320, if you just want to look at that by itself, I did this. Just like we were doing the other ones. Fifth root of 32 is 2. Fifth root of 10, I don't know. So there's your 2. There's your fifth root of 10. You do the part you can. You leave the part you can't.
And then how is there 2 A's though? Generally 1.
How do you mean when you say that? When you say, how do you mean?
Because
I agree. Yeah.
doesn't say
Once.
one.
So here's 1
So that's
with 1 left. And again, another way to look at this specifically. How do I write that in fractional power form? It would be a to the what power? What's on the bottom? 5. Roots are on the bottom. Well, I want to rewrite it into fractional form, right? Fractional exponent form. It'd be a to the 6/5. I would never do this, but I'm just showing you why this works. 6/5 is what as a mixed number? 1 and 1/5. So you have a whole A, bam, and 1/5 of an A, bam. So
It just gets kind of, yeah, I understand. It's just, I know I'm gonna have a.
but I don't want it to be, here's the thing about math. If you understand, it's not as much memorization as it seems. Everybody always thinks all math is memorization. That's crazy. It's if you understand why something works the way it does, you're not really memorizing it then. You just understand why it works. You can free up some space in your brain for other shit. Right? Like the classes where you actually have to memorize stuff, like anatomy or something. I don't know which one's going to take. So, what's this? Real quick, what's that? Is everybody cool? That's A. So if I throw another A in here with this, isn't it going to have to stay there? I can't do anything with the other A. How many A's do I have to throw in there so I'm able to get no radical left? That's a weird question. I'd have to throw 5 more A's in there, don't I? I could do the 5th root of A10. What's that? A squared. But look at all the stuff in the middle. All the stuff in the middle is going to have to be between 1 and 2. It's going to have some fractional stuff left over. So the 5th root of A6. Well, shit, I can do the 5th root of A5, but I can't do the 5th root of A. So that's A, 5th root of A. Just like I have here. A, 5th root of A. Right? Any extra stuff in there has to stay in there. I can't do anything with it. Yes?
The way that sort of makes sense to me is sort of like division, so that what's left inside the radicand is
Exactly.
remainder.
That's the beautiful
So
thing
you
about
take it out and then the remainder.
the remainder. What remains inside. I like it.
Like division.
It remains. So yeah, exactly. That's why this works. 5 goes into 6
6 once.
once
Goes out
with 1 left over. Now that's a nice way to do it, as long as you at least have been exposed to why it works. I have no problem with something like, obviously I have no problem with something like that, as long as you understand why it makes sense that it works. Yeah.
3, the second F.
Oh, I love it. Yeah, so it's pretty obvious that I Frankenstein this together from past, and I didn't really sew my seams well here. So the second F, the one with the 8 in it, right? The 8 next to the 2/5. Who is asking that? You? That one, right?
Yeah.
Okay.
Just want to check.
Alright, so what's the main thing happening here? The order of operations would say do inside first. There really is nothing I can do inside except take him down. And that's, you could do that. But when I have a negative power on the outside and I bring it in, isn't that going to become positive on the next step? Right? So there's 2 kind of ways to do this. And the way I actually recommend doing this is just to start distributing this thing through. And then seeing who's really negative and flipping. So you would get, what would happen to it would be a to the negative 2/3, and I can worry about that on the next level, right? Times x to the, what's the negative there? What do you do with powers when you raise them like that? Multiply them, right? So again, don't let the fractions themselves freak you out. You know the properties. When I raise something with a power to a power, I multiply the powers. So what do you get when you multiply those?
Minus 4 over 15.
Negative 4/15. And what happens with this?
Plus 6 over 2.
Yeah, the 3's cancel, the negatives cancel, you're left with a 2. Yes, ma'am?
How'd you get the negative 2/3 on
So what's 2 to the 4th power? That's kind of too easy. 2x to the 4th power. What would that be? Good. Where'd that come from? Because you got to raise each piece to the 4th power, right? So you got to raise each piece to the negative 2/3 power. So I did.
So why do you got a 2 again? Because you divided it.
What do you do when you raise something with a power to a power? You multiply the powers. What's negative 3 times negative 2/3? The 3's cancel. Negatives cancel. Right? Do you have to do it all on one line? No. I mean, if you want, this will be 6 over 3, and you'll see it's 2 on the next step. Right? So these two have to do what? Go on the bottom. And what's the only piece I can do any more with? What's the only piece I can? It's not a trick question. There is something I can still do something with. I can do 8 to the 2/3, right? How do you rewrite 8 to the 2/3? How would you rewrite that using a cube, using a power, using a root? Yeah, cube root of 8 squared. Good. So you do the 2/3 power, and you know how to rewrite the power, so you can make it look like a root. 3rd root of 8.
Is that the only way you could do that? Or is there another kind of way?
There is another way, if you like it. 8's made up of 3 2's. If I take 2/3 of those, I get 2 2's, so I get 4. Is it always easy to think that way? No, because what if it was to some, heinous power? Right. That's what you're going to end up with. What's the cube root of 8?
2
squared? 4. Yeah. You good? Okay. So really, the main thing here is to realize this problem is really just applying the power to each piece. And again, if you really want to, you could do like I did here. I just put the power on it and then worried about doing it later. So I didn't have to do too much in my head as I went. So if you actually want to take that a little further and say, okay, 8 to the negative 2/3, x to the 2/5 times negative 2/3, y to the negative 3 times negative 2/3. I mean, that's really what's going on here. That's applying strictly the property. Just the property of multiplying by the power. I haven't done anything else. Absolutely nothing else have I done. So then on the next step, I can start doing this. And I can start attacking that like we did. Right? Nothing wrong with this. Except it takes a little more time. But yes?
And this is a question. I make the root from the beginning, from the first step. I put 1 over root. But I don't know, right or not.
Yeah, but then the cube root of x to the 2/5, you kind of have to rewrite it again to work with it, right? I mean, I definitely don't want to look at that. Does it make sense?
Yeah.
Yeah, so there's a lot of other ways to do it. You could have brought that y to the negative 1/3 down first, and then flipped it, and then did everything to the 2/3 power. That would work too. There's a lot of different ways you can do this. As long as you can do it one of those ways. Yeah.
1e.
Did you have a question up here? Did I forget you? You're good? 1 e. This is the kind of problem with it's got that things are almost the same, but they're not quite the same problem to it. What the hell am I talking about? Let's see. So as we go through this problem, can we do it so I don't have to rewrite it and rewrite it? What can I do on the top of that first fraction? Take a b out. Okay. So if I take a b out, so that was just GCF.
Okay, like the way I've been doing it is I've just been doing the difference, the sum, or the difference of squares.
Question. Okay, I'm glad you said that because I have a lot of people that, there was a problem like this, and then I got somebody tell me that factor is like this. Now, again, if you're that person, I'm not. necessarily come down on you because I've seen this before. But do you see where they got that from? You can kind of see where that came from. But why does it make no sense at all? What's this? 0. So you're saying that that's always equal to 0. That doesn't make any sense. Plus, is y times y equal to y? No. So there's a couple quick checks to tell yourself that's not right. If it's 2 terms, it's not going to be like that unless it's the difference of squares. Is it? Is that guy squared? No. So what's always going to save your ass from this kind of mistake is you always look for GCF first. Right? Because it's either the only thing you can do or it makes the problem easier. And in this case, it's the only thing. And the same thing here. That's definitely not a square. That guy's cool. It's a difference. That's cool. This doesn't have 2 parts to it. Right? 3b. There's not 2 3's, 2 b's. So this would just be a GCF. Just take a y out. Cool. So that's why that's the way it is. Because it's just, they both have a b, I can take a b out. What do you do on the bottom?
Group.
Grouping. First 2.
B minus 3.
So maybe I should write it. So what comes out of the first 2? Yeah, b squared. B minus 3. Now to make that look like that, what do you actually have to take out? Yeah, so you can actually take a minus 1 out if you want to make it even better. So those signs changed. Now I know I'm on the right track. I know it's legal for me to go on because those are the same. So what's the last piece for that bottom?
B minus 3.
Or actually the second to last piece. Because then that can go further. Oh, I'm so evil. But you know this. You know when you factor something, you have to take a real quick second and just make sure, does anything else go further? So if I said completely factor 18 and you said 9 times 2 and you stopped, that wouldn't be right. You didn't take the 9 further. You've got to make sure if anything else goes further, and this dude goes further. B plus 1, B minus 1. Cool. And this is actually not a bad idea. I saw a few of you guys that came out to the Friday session, and trust me, this is obviously a big problem for me too. Organization and knowing what the hell is where and all that kind of shit. And when you try to do the whole problem at once, it gets a little crazy. So see how I focused all my attention for a minute on that bottom dude. So now I'm going to rewrite the problem and just put where I ended up. So now we can focus our attention. It's very cool with this division, so I have to make it. Yes, ma'am.
You don't have to change, like, you know how you do -1, how it changes how it flips. You don't have to do that. See how it's,
We're going to do that on the next, because we didn't see it till right now, right? So now we're going to do it. Yeah. So I have to flip this. Let me go ahead and write it again here. Okay. So I think, yeah, I'll do this the full way out, and then I'll show you the shortcut you could possibly look for in this kind of problem, right? How do I factor the top here? Let's focus on the top.
Also groups.
Yes, almost, well, I gotta do one little thing to it before I can make it grouping. I have to,
Multiply 8
yeah,
by...
so take 8 into account. Multiply 8 by -19.
Yes.
And what do you get?
No. 8 plus 19.
No, you can't even go there yet.
No.
So 8 times -19?
Yeah.
Negative 152, is that right? So I need factors of that make 11.
Yes. 8, 19.
8, 19?
Yes.
Yep. That's nice. You always kind of look for that because you know that one factorization of that number, whatever it is going to be what you just did. So it's not a bad idea just to take a second to make sure, do those work? Right? And the 8 and the 19 will work as long as which one is positive?
19.
The bigger one's got to be positive, but the 8's negative. What do I do with those two numbers now?
You plug them in.
Plug them in where?
Where
Yeah.
the 11?
Alright. you got to keep an eye on me because
Is it
what am I missing?
B.
Yeah, this does not equal 11b. But again, I saw a few people do that. You gotta, this just gives you the coefficients. You have to put the variables on them. These two have to become this. If they don't have b's on them, they're never going to become 11b. Right? And now, of course, I've set it up so that I can group. Yeah, so out of here comes 8b. B minus 1, good. Out of there comes 19. I know I'm on the right track because I got two of the same thing there. So last step on that one is. So now I can rewrite this top as that, right? Just a little 1 there. So you notice a really good way to do these multi-part problems is to actually tear them apart. Take the first part, work on it, take the second part, work on it, and then you're going to slap them all back together. Because good God, trying to keep track of everything as it goes through gets a little crazy. Yeah.
I put the 19 in front and then the A.
So you did you do this?
Yeah.
Good, I love it. So real quick, I don't think we've done this in here yet. All we did was rewrite the middle. So this process says these two will work, guaranteed to work. And of course, math says, I don't care which way you put them in there. So it still has to work. And if you do this when you get b minus 1. See how your 8b plus 19 was on the outside, now it's on the inside? B minus 1 was on the inside, now it's on the outside. But I don't care because the last step makes it all the same. It's still the same at the end. Cool. And how do I factor the bottom here? Thankfully, it's a little easier.
2b move.
Yeah, 2b.
A, B, 19.
Now, if we would have done this one first, again, I don't know if you guys, a few of you guys might get this. I mean, is everybody cool? All we're doing right now is we're factoring each part so that we're able to see what dies, right? With the violent form of math that I teach. If I would have done this part first, before I did this ugly thing, I actually get a huge clue. Got a raging clue. Right? A huge clue as to how to do the top. Some of you guys got that right. And if I write down, if I say, okay, let's say 8b plus 19 is a part of this. I'm just going to assume that it is. How do I know that that might be true? There's an 8 there. And the whole point of this problem is to have stuff cancel. So like, Jeff made this thing up. Let's see. Maybe 8 plus b 19 goes in there. What would have to be here to make 8b squared?
1b.
B.
B minus.
And to make negative 19?
Minus.
Isn't that the freaking answer? Wasn't that a lot quicker? Right. And again, there's always a quicker way to do things. And quick is good because then you have more time for other stuff. But if you don't understand the quicker way to do things, you've always got to back up, do it the old-fashioned way, right? Not a damn thing wrong with this, really, because you need practice on that anyway. What the hell? So now let's put things back together. I've got, and what did we figure out we have to do there?
Minus 1.
Taking negative 1 out. Times. Now we figured out what that is. And we got what that is. So it's a little easier if you break them all up. Treat them like 4 different problems, and then bring it all back together at the end. And now you can just go crazy, right? What dies? B minus 3.
Minus 6.
B minus 1. AB plus 19.
Yes.
B.
Like,
B minus 3, yeah.
wasn't it?
We took a negative out, so it became that. Yep. That was the next step I did here. Cool. So what's left alive on the top?
Minus 1 over.
Yeah, there's a negative 1.
Yes, minus
Is everything divided, so you're left with a 1 at the end. Over
2.
2,
B plus 1.
Plus B.
B plus 1. Yeah.
I
I still don't get b minus 3.
Oh, so, let's see. So you're cool with it right there, right? Let's just focus on this first piece. In fact, let's just focus on that. There's other shit there, but it doesn't matter. Will these cancel the way they are? No, they can only cancel if they're the same. But they're almost the same, right? This one, the b's negative, here's positive, the 3's positive, here's negative. So really, they're just offset by a negative sign. So if I take a negative 1 out, the b should become positive, the 3 should become negative now. Right? And now I've made them the same, now they'll cancel. Could I do that sort of thing on this? Can I make that work? No, because the y's are the same. If I took a negative 1 out of either one, they're going to kind of like pass each other. No, the 7's are the same. I took another negative 1 out. Now the y's are the same. You'll never stop. I mean, it's crazy. So they have to be completely opposite. They have to have everything in the negative. So when I take a negative 1 out, it goes back to the same. So they make kind of a big point of that in the book.
I have a quick question. You know how there's a radical fraction, and you said you know get rid of the fraction, like get rid of the root at the bottom.
Yeah.
And let's say you subtract the bottom by the top, and there is a root. Would you subtract the inside? Would you multiply the inside?
All right. Let's see. Let's set up an example of what you're trying to say.
Let's say it's like 12 and 6. 12 root 12, like the root side, whatever. I don't know. Yeah, that. And then the 6 with the root under.
Underneath it?
Yeah. 6, yeah. And then would you times it, let's say you want to make...
No, real quick. On this problem, I would divide and be done. Right? Because square root of 12 divided square root of 6 is square root of...
Okay, well, let's say you couldn't divide it. I'm just...
Alright. Like that? Or maybe...
Let's say...
I think I see what you're saying.
Yeah.
Jeff, no, that's the one. There.
Yeah.
Alright, so what does this bottom need? Another 6, right? To complete him. He needs one more 6. So whatever you do to the bottom, you got to do this top. God, I can't speak there. I'm getting sick again. Hello. You got to do to the top whatever you do to the bottom. So on the top, what do you get?
So that's what... So you...
Square root of 30. And on the bottom, you get a nice whole 6. Yeah. So the top just has to happen to it. It's the same thing, really. Your whole focus on this kind of problem is to make the bottom the same. So you're going to multiply by 3, and then the top just has to get the same damn thing.
So if you could divide it, it's like that one, you could just leave it, and you just...
Yeah, and you're done. No need to rationalize, because you cancel the radical directly. Right? Rationalization is all about getting rid of a radical you can't get rid of. Otherwise, here, I killed it by just dividing it. The bottom's gone.
Like if cubes are squares, and then if it could be, like, if it could go into it, then you would keep going, and you could cancel, that's the answer. Let's say if it's like a cube, then that it would just be like 3, like the root cube 2, then that's just the answer.
Wait, what?
Okay, let's say like on the top and the bottom, you know, there's like a 3 at the corner of it.
Okay.
Then that would just be the answer. Let's say you divide like 3, write everything the same, just put the 3's, and then you divide the 12 and the 6.
Yep.
Would it just be 3 and that, because the 2 can't go into the 3, right? Right? That's the answer.
Well, you can't do the cube root of 2 because you only have 1 2 inside. Yep. The whole idea of a cube root is it needs 3 somethings to go further. Now we know, right on the heel of that, I know the cube root of 2 is something. 1 point, blah, blah, blah. But when I say that, I mean, can I break this up as whole numbers? Can I get 3 whole numbers that multiply by 2? No. Never.
So for 3b, just divide and then put the cube, and then that'll be 3 cube 8, and then break.
Well, the cube root of 8, yeah. And then you just, cube root of 8 is 2. Yeah.
Can you do F? 1F?
Let me do this. Let me give you guys the answer key. Because like I said, I think it's 6C, number 7, and number 8 that I want to do on the board because I didn't put it on the answer key. Because I got to the bottom and I got tired. I didn't want to waste ink. And don't forget, if you weren't here last time, I forgot, number 5 on the practice test is from section 12.6 in the white book, section in the blue book. We didn't get there yet, so that won't be on this test. It'll be on the test after this one. The number 5 problems, we're not going to have anything like that on the test. So let's do this. Let's do real quick 6C, 7, and the 2 problems, number 8 references. If I were you, I'd probably just put them on the back of my answer key so it's all together.
6 and 7?
Number 6C and 7 and 8. So you know I'm going to give you one like this. Either it's going to be an absolute value, that's a quick answer, or absolute value inequality or equation, that's going to be a quick answer. Of course, here you got to realize what should you do first.
You know, move the.
Is my absolute value by itself?
Divide 2.
No.
Minus 2.
I definitely would not do this.
Minus.
I can only cancel multiplication by division. Yeah. So then I get 3 minus 2x, absolute value.
Flip the sign.
Good. Less than -1. And that's a quick answer. Should be. You could set up your 2 cases and all that and go insane and think that you're getting answers, but right here you can tell what the answer is. No solution. You can't have an absolute value be less than a negative number, right? So that's an example of stepping out of the process for a second. Just looking at what the hell you got. Does it make sense? Does it go anywhere? Does it make sense to go somewhere with it? I mean, here it doesn't make sense to go any further. That can't happen. No solution.
That's the only time there will be no solution.
Yeah, if I say absolute value is less than a negative number, or even just less than 0, we know that can't be true. An absolute value has to be at least 0, right? Yeah.
No. I was multiplying by dividing the -2 and -2 divided by 1.
Yeah. Yeah. So that's 6C. That's one that I don't have in the answer key. Number 7. Let me ask you this. To graph that solution, and a lot of you guys do this in very different ways. Some of you guys find the y-intercepts and the x-intercepts and go from there. I'm always going to solve for y, especially because of the way that I don't use test points. And if I solve for y, I can always tell, am I going to shade up if it's greater, am I going to shade down if it's less than? Right? So if you find intercepts and do that, that's beautiful. Keep doing it. I love it. I'm not going to do that. I don't want to. Then, so if I solve for y on that first dude, I get that. Is that cool? So the 3x minus y greater than 4, less than 4. Subtract 3x if you want to. And then of course you have to divide by -1, which means the sign flips. Those negatives go away. That becomes minus. Cool. Real quick, if any of you guys get this, what I actually do, if I'm going to solve this, I add the y over, subtract the 4 over. They effectively change places. And then I since y, if you read this backwards, y bigger than that, y bigger than that, bam. Right? Force your y to become positive first. You don't have to worry about flipping the damn sign, because a lot of you guys still forget to do that. And then solve in the next one, hopefully that's a little more. So subtract the 2x, divide by 3. So I get that there. So you can double check me, you can solve for y yourself. Make sure I got it right. Cool. Now how do I plot this first dude? Good. So -4 is the y-intercept. And the slope tells me to go up 3. 1, 2, 3. Over 1. And what kind of line am I going to use? Dashed. Dotted. However you want to say that. You can use a test point. If you plug in 0, 0, is 0 bigger than -4? Yes. What's funny to me is I get a lot of people do that. They do it beautifully, and then they say false. And then they shade it the other way. But come on, look at what it says. 0 is bigger than -4. Of course it is. Which means I would shade in the direction of the test point that I used. That's the whole idea there, right? If that test point works, everything on that side works. Me, greater, up. I just like quicker ways to do things. This guy, well, how could I graph him? Y-intercept is 3. 0, 3, I like it even better. And then the slope says, yeah, down 2, over 3. What kind of line am I going to use? Solid. Right? Test point you could use is 0 smaller than 3, yes. So I'm going to shade in the direction of the test point, or just less than, so I'm going to shade down. So where's my answer? Where these two cross. So just take a second and make it a little darker. Kick ass. Make sure you make it really clear to me that you're shading in something darker. If I don't see that, I'm going to say answer, question mark, and take some points off. So the answer is going to be in this region here, right? Yeah.
Hey, I got that wrong on one of the quizzes. So the answer is always going to be where the two shading parts overlap.
Exactly. Cool. So the answer for a system of equations is where the two lines overlap. The answer for a system of inequalities is where the two shadings overlap. Same kind of idea. Because those shadings represent everything that works for that line. What works for both is where both shadings are. So then you just kind of shade it in a little darker so I can tell you know that's where the answer is. Okay, cool. And some of you guys might even be my color pencil people. That would be awesome. I am not a color pencil person at all. But if you are, let it out. Do it. Teachers love that kind of stuff, even though I wouldn't do that for myself. Be nicer to me than I would be. Okay, so that's number 7. And now number 8. All right, so 8, number 22 says this. Copy Quick has 2 copiers. One can copy in 20 minutes a report, and the other one can copy in 30 minutes. How long would it take both machines to do it working together? Yeah, I can do one job in 20 minutes. The other guy can do one job 30 minutes together. It would take us how long? Yeah. Say again? 12 minutes? Maybe. How do you solve it? Yeah. So LCDs will be 60, X 11. So then, if you want to, you can multiply this by 3X. This guy needs 2X. And this guy needs 60. So all the bottoms go away now because it's an equation. I can kill them. So I multiply both sides by it. So they get 3X plus 2X equals 60. 5X equals 60. Cool. 12 minutes. Not too bad. 20, what was the other one? 24?
24.
Oh, yeah. So 24 says Ryan drives 20 kilometers an hour faster than Alicia. So the same time that Alicia drives 225 kilometers, Ryan drives 325 kilometers. Find the speed of each car. This is a very quick summary of what that said. So Ryan drives 325 kilometers. In the same time it takes Alicia to drive 225 kilometers, and Ryan's going faster, so that all makes sense. Thank God, you should make it further. How the hell do I set this up? So I can make a little box if I want to. You don't have to if you don't want to. There's a decent organization thing. Right? I've got Ryan, I've got Alicia. Rate times time equals distance.
The same time.
The thing I know for sure is Ryan went how far? 325 and Alicia 225. The thing I know next is good is who's going to be just X as far as their speed. Good. So if Alicia's X, Ryan is X plus 20. Careful. He's not going 20 times as fast. That would be, I'd hope Alicia's going pretty damn slow. Right? He's just going 20 times faster, so it's plus. And the equation's going to come from what phrase up here? In the same time, 11. So you're going to find the times and set them equal to each other, right? If they would have said in a total of 8 hours, maybe these two add up to be 8 hours or something. You kind of with me? So the equation almost always comes from the distances are the same, or the times add up to 7 or something. So in this case, how do I write the times for each of these? What's the time for Ryan?
D over R.
Yeah, D over R. So 325 over X plus 20. Same way for Alicia. Because again, if rate times time is distance, then time is distance divided by rate. So then your equation comes from setting those equal to each other. And this is the one time you're really allowed to directly do what? Cross multiply. Especially because these don't have anything in common. Don't tell me they have X in common. No, they don't. When I say that, I mean a factor. And this doesn't have X as a factor. So now you can just cross multiply. Oh, what's 20 times that? Yeah? And then subtract, divide. Alright. 45 kilometers an hour. Who's that? Alicia. So Alicia's going 45 kilometers an hour. So Ryan's going 65 kilometers an hour. Cool. Which is actually slow. I went to Canada and I felt like I was racing because you're going like 130 kilometers an hour, but not that fast. It's like 60 or 70. How are we doing? Is that all right? Okay. So those are the three that I left off the answer key. So now we can talk about whatever you want to talk about. Yeah.
Okay. The answer we got for 45 kilometers, what is that? How do you know?
Say again?
How do you know what's that answer? Oh.
So it's the rate that Alicia was going.
Okay.
So once I set this up for myself, it actually helps me answer the question too. Once I get X, I can see right where it is. That's Alicia's speed. So Ryan's speed must be 20 more than that.
Okay.
Cool. Yeah.
32 from 74.
Oh. Oh. This is the McKeague book, 7.4. There's a couple different ways to do this. But I know at some point, in order to add these fractions, what do I need? LCD. So you can either give them the LCD first, or you can do something to this guy first. Does that make sense, what I just said? Because you know at some point you're going to have to rationalize this. But you also know at some point you're going to have to get an LCD between the two of them to put them together. So which way do you want to do first?
LCD.
LCD, okay. So what's this guy need? Yeah, on the bottom he needs square root of x. Cool, so you multiply top and bottom by square root of x. And again, don't let the fact that it's square root of x bother you at all. This dude has a 1 on it, so whatever the hell he's got, he needs. So that they have the same thing. It's that simple. This could have been some heinous thing, and I just give him the same heinous thing. So what on top, what happens?
X.
Sweet. So you get x over root x plus 1 over root x. X plus 1 over
X. 2.
That's a is it a minus or a plus? It's a plus. Good. All right.
Square root x.
Yes, thank you. All right, square root of x. When you add two fractions, you don't change the bottom. The bottom is kind of like the like term part. You have x of these plus 1 of these is x plus 1 of these. I'm not multiplying. I'm not doing any of that. So the last thing I have to do in this problem then is rationalize the bottom, and of course, what does the bottom need? Yeah, he needs another x. Yeah, so I give him radical x, radical x. So on the top I get x plus 1 times radical x. On the bottom I get x. Looks gross. What can you definitely not do that you think somebody might do?
Cross out the x's.
Cross out the x's, and you know you can't do that, all right? Or hopefully you know that. This is a plus. Can't break into that. So that's it. That's your answer. You can distribute the radical x. Does it help you? No. So don't. Yeah.
I was looking at the answer sheet, and I think you're missing one in the 3.
Okay, that could be true. A, B, C, D, E, F, G. Oh, E, F, G.
You have like 6 answers, and there's 7 questions in the section.
There's actually 9 questions in this section. And I have 9 answers, so that's good. Right, 3A, B, C, D, E, F. And then down there is 3E, F, G.
Oh, okay.
Yeah. My answer keys, I just use space really well. And then you see what I do. If I'm done with one piece of paper and there's not that much left to do, I'm going to do it in class. I'm not going to use another side. Screw it. Yeah.
3E.
3. B?
E.
E. Which E?
First E.
First E, okay. Okay. So this is definitely not x plus radical 12x plus 6 or something. If you were thinking along those lines, I just want to stop you right there. Because a square root cannot go across an addition or subtraction. They don't play well together. Right? This is not 2 plus 3. This is square root of 13, not 5. Okay, good. So what the hell can I do here then?
X plus 6, X
Move,
plus
Yeah, this is screaming to be factored. And of course, x plus 6 times x plus 6 is x plus 6 squared. And what did the square root and the square do? Cancel. Now, I think on the test, I'm not even going to worry. In some cases, you have to do this. But I'm pretty much going to say don't worry about that. Just assume that everything is positive and go for it. Yeah.
In what cases do you have to put the absolute value?
If they don't say that kind of thing, so technically I should put it on there. But I figured I'll just talk about it in class and not worry about it. If I don't say a damn thing here, you have to put the absolute values there. But on the test, I'm going to say, assume everything's positive.
Because I know doing homework, there's a couple of times I thought it needed it, and I looked up the answer and it didn't have it.
Because at the beginning of that section of homework, they probably said, assume all the radicands are positive things. Yeah. They probably didn't say it exactly like that.
You have to get in the correction if you said assume all of them are positive.
Yeah, exactly. Yeah.
But otherwise, you're all...
Otherwise, you have to put the absolute value when it's an even root, right?
Okay.
If it's an odd root, you don't have to do it. They're cool with negatives. Yeah.
For the test